In this video, I'm going to go through the first midterm review packet that's all about transformations. So for number one, it says, if A prime, B prime, C prime is the image of triangle ABC, under which transformation would the triangles not be congruent? Remember, if the triangles aren't congruent, that means when you transform them, you did something that wasn't a rigid motion, which, remember, rigid motions preserve angle measure and side length. So a reflection's a rigid motion, so that can't be it. A translation, just moving something left, right, up, down, that's a rigid motion. A rotation, spinning something around, is a rigid motion. But a dilation, centered at the origin with a scale factor of 2, remember that's, let's say if I've got that triangle, and then I dilate it by a scale factor of 2, it would double in size. So all of a sudden these side lengths are no longer congruent. So anytime you have a dilation, the images will not be congruent. Similarly for number 2, it says the vertices of triangle JKL have those coordinates, under which transformation is the image not congruent. And again, a rotation, a translation, and a reflection are all rigid motions. The only thing that isn't is a dilation. Number 3. In the diagram below, a square is graphed in the coordinate plane. A reflection over which line does not carry the square onto itself? Well, let's try a couple of these. For x equals 5, that's if I go right 5 and draw a vertical line there, well, I can already see that if I reflect over this line, this square is going to end up on this side of the line, so it's going to be somewhere over here. So it's not going to land on top of itself. So I already know that's the answer. But if you wanted to check a couple more of them, y equals 2 is just going up 2, that's the horizontal line there. And that's a line of symmetry for the square. So if I fold it over, this side is going to land on this side is going to land on this side, and so on. For y equals x, that's that diagonal line that goes straight through the origin, where all the x and y values are the same. So that is also a line of symmetry along the diagonal. And then for number 4, if I end up subtracting x on both sides, I'm left with y equals negative x plus 4. So that's a line with a y-intercept of 1, 2, 3, 4, right up there, and with a slope of negative 1. Of course, you could always type that into your calculator. And that goes along the other diagonal there, and that's also a line of symmetry, so the square would carry onto itself over that transformation. For number 4, a sequence of transformations maps rectangle ABCD onto rectangle A double prime, B double prime, C double prime, D double prime, as shown below. And it asks which sequence of transformations is going on here that maps this to this and then this to this. Well, remember that the corresponding vertices need to match up. So D needs to end up at D prime and C needs to end up at C prime and so on. So this first transformation looks like I reflected it right over the x-axis. So I know it's got to start with a reflection, so I could rule out 3 and 4. And then to get from here to here, it looks like I spun it in a counterclockwise rotation, so that's going to be a reflection followed by a rotation. Number 5. Which regular polygon has a minimum of 45 degrees to carry the polygon onto itself? Well, remember, an octagon has 8 sides, a decagon has 10 sides, hexagon has 6, and a pentagon has 5. So what you could do to check is you could take 360 degrees and divide it by the number of sides, and that's going to tell you the minimum degree rotation for it to land on top of itself for all those sides to line up again. And if you take 360 divided by 8, you get 45 degrees. So it must be that it's the octagon that takes 45 degrees to carry on to itself. And you could try that through all of them if it's not answer choice 1. You could divide 360 by 10, divide 360 by 6, and so on. Similarly, for number 6, it says which rotation about its center would carry a regular decagon, remember that's 10 sides, onto itself. Well, if I take 360 degrees, a full rotation, and divide it by the 10 sides, every time I spin it 36 degrees, I'm going to end up right on top of itself again. So the idea is all of these are not multiples of 36 except for one of them. So a 36-degree rotation would land on top of itself, but so would a 72-degree rotation. That's just 36 times 2 36-degree rotations. So what you could do here to quickly check is you could divide all of these by 36 and see which one gets you an even integer so that it's a multiple of 36. And when you divide 252 by 36, that's 7 rotations of 36 degrees, so that would land the decagon right on top of itself. The rest of these are going to be decimal answers, so they're not full 36-degree rotations. Number 7. On the graph below, point A at 3, 4, and segment BC with coordinates 4, 3 for B and 2, 1 for C are graphed. What are the coordinates of B' and C' after BC undergoes a dilation centered at point A with a scale factor of 2? So if we're dilating centered at A, then points A and points C are going to move either further away or closer to A based on their distance away from A that they are right now. So for example, if my scale factor is 2, I want to double that distance or multiply it by 2. And if I look at the distance B is from A, I would have to go down 1 and right 1 to get to B. So if I double that, I would go down 1 again and right 1 again to get B'. It looks like those coordinates are, I've moved 5 to the right and 2 up. To get to C from A, I would have to go down 3 units and left 1. So to double that, I'd go down another 3 units and left another 1. To get C' right there, it looks like those coordinates are 1, -2. So that's the best answer choice there. Now, you'll be able to check to see if you did a dilation correctly, because if you connect your image points, you should notice that what you ended up with is roughly parallel to what you started with. Mine's a little bit off here based off of how I connected it, but it should also be twice the length. So if I were to count the length from B to C using the distance formula, it should be half of what B', C' is. And it looks like that's about the case here. Over a line, triangle A', B', C' is the image of triangle ABC. Explain why triangle ABC is congruent to triangle A', B', C'. Well, you know a reflection is a rigid motion. So the first thing you could say is that a reflection is a rigid motion, and rigid motions preserve distance and angle measures. So that's a phrase right there that's going to be helpful anytime you're talking about rigid motions and congruency. So the side lengths stay the same and the angles stay the same as well. For number 9, triangle ABC is graphed on the set of axes below. Graph and label triangle A', B', C' after it's reflected over the line x equals 1. So that's just a vertical line where all of the x values are 1. So here you could just count. B is 1 unit away from the line, so B' would be 1 unit away. C is 1 unit away as well, so C' would be 1 unit away. And A is 1, 2, 3, 4 units away, so if I count again, 1, 2, 3, 4, A' will end up right there. Now, you'll be able to tell if you did this correctly because a reflection's a rigid motion, so these two triangles should be congruent. So if they don't look congruent, try graphing it again. Number 12. Number 10. In the diagram below, triangle ABC has those coordinates. Our task here is to graph and label triangle A', B', C', the image of triangle ABC after a translation. It's going to be our first transformation. 5 units to the right and 2 units up, followed by a counterclockwise rotation of 90 degrees about the origin. So let's start with the translation. That's probably the easiest transformation we could do. If I want to go right 5, I could just take where A is and count 1, 2, 3, 4, 5 to the right. And if I want to translate 2 up, I could count 2 units up from that. I'm going to do that to B and C as well. If I take B and go 1, 2, 3, 4, 5, 1, 2, that's where B' is, that's where A' is, and C' is going to be 1, 2, 3, 4, 5, 1, 2, right there. And you'll know if you did this correctly again because your triangle should be congruent, right? All we're doing here is a rigid motion. And I know that that preserves distance and angle measures, so these triangles shouldn't change shape or size. Now, those lines I connected them with were a little thick, but that should be about what your triangle looks like. Where, not our final answer here, but what we have currently, we've got A prime at 1, 2, 3, 4, 5, 6, 1, 2, 3. B prime at 9, 3. And C prime at 9, I think that's 7. 1, 2, 3, 4, 5, 6, 7. Now I'm writing those down for a reason. Because I know my next transformation is going to be a 90 degrees counterclockwise rotation. Remember that a 90 degree rotation is going to take a point x, y and send it to negative y, x. Just as a reminder, for 180 degrees, that's going to be negative x, negative y. And for 270, that takes a point and it changes it to y, negative x. But the one I care about is 90 degrees right there. You could always turn your paper 90 degrees and try to visualize if you're going in the counterclockwise direction, your triangle should, it should look something like that over in the second quadrant there by the time you're done with it. But I'm going to apply the bump switch rule here to all of my primed coordinates here. So a double prime, I'm going to move that 3 to the front and change the sign. That's what negative y means. Doesn't mean necessarily make it negative, just means change the sign. So B double prime is going to be at negative 3 if I bump that 3 to the front and change the sign, 9, and C double prime is negative 7, 9. I'll take a minute to plot those points. Going left 3 and up 1, 2, 3, 4, 5, 6 for A double prime. Going up 3 more for B double prime. And there's C double prime. Now always ask yourself when you're doing a series of transformations, do my triangles look congruent? Does this look like a 90 degree counterclockwise rotation about the origin? The answer to both those questions here is yes. If you want to visualize it, what a rotation is doing is it's taking the distance from, let's say, A prime to the origin, and it's rotating it 90 degrees, just like that. So when I connect them, that should look like a right angle if I rotated 90 degrees, and those distances should look the same. Number 11. On the set of axes below, triangle ABC is congruent to triangle STU. Describe a sequence of rigid motions that maps triangle ABC, this one, onto that one right there, triangle STU. Now, this looks like I'm going to have to rotate at some point. And believe it or not, if you just rotate this around the origin 90 degrees counterclockwise, that's all you need to do here. If I look at the point A, and I write down those coordinates, it's at negative 2, 1, 2, 3, 4, 5. And that point, when I transform this triangle, should end up at S. Just if I'm looking at the order of the letters there, that's the first letter in both of those triangles. And the coordinates for S are negative 5, negative 2. Now, if you remember from the last problem, that's actually just that transformation happening where you're putting that y in the front and changing the sign. So a sequence of rigid motions could just be one rigid motion. That's all you need. In this case, I'm going to do something that requires a little bit more just so that we get some practice describing them. If my triangles aren't touching, usually translation's going to help me. I know point B should match up to T, so I would have to translate down 1, 2, 3, 4, 5, 6 units and right 1, 2 units. So if I wanted to start by translating triangle ABC down 2 units and right, down 6 units and right 2 units. And here's where my triangle would be. I'm just going to sketch it so we can visualize it. if that's where B prime is, C would be 1, 2, 3, 4, 5 units vertically up from it, and A would be down 1 and right 2 from C. Just so we get an idea of what it looks like here. Now visually, I know we said that we could do this in one shot with a rotation around the origin. We're still going to need a rotation here to kind of have C prime B prime lie on UT there. I know that's a 90 degrees rotation. I know that direction is counterclockwise, and the point I want to rotate around is T. And the coordinates of T right there are, I go left 2 and down, what is that, 1, 2, 3, 4? Let me count. Down 4. So, in order to get this to land directly on top of that, we can rotate. That's the transformation I'm doing. I'm going to say how much? 90 degrees. I'm going to give a direction counterclockwise. And then I need to state a center of rotation. So rotate 90 degrees counterclockwise about point T, which I believe is at -2, -4. So if I have the numbers to use, I'm going to reference those. Triangle MNP is the image of triangle JKL after a 120 degrees clockwise rotation about point Q. So I know these two triangles are congruent because that's origin motion. So it says the measure of angle L is 47 degrees. First thing I'm going to do is label my picture with that. And N is 57 degrees. Determine the measure angle of M. So that's the first thing we're going to do. Well, if I'm thinking about this as a rotation, L should coincide with P if I were to rotate this back. So I know angle P also has to be 47 degrees. And now if I want to find that missing angle of a triangle, I know the triangle interior angle should sum to 180. So if I do 57 plus 47 to get 104, and then if I subtract that from 180, I find that that missing angle should be 76 degrees. So the measure of angle M in this case is just 76 degrees. Now the question is, how would I explain how I arrived at that answer? Well, you would do exactly that thought process where you would say, oh, okay, so a rotation is origin motion, so triangle NPM must be congruent to triangle KLJ. Be careful about the orders of your letters there. N should go with K, P lines up with L, and M lines up with J. And then you would say, since it's origin motions preserve distance and angle measure, so the angles must be the same, so angle P is 47, and then the interior angle should be 180, so you subtract it from that to get M. Number 13. The grid below shows triangle ABC and triangle DEF. Let triangle A prime B prime C prime be the image of triangle ABC after a rotation about point A. So I'm rotating about point A, so I know point A is not going to go anywhere. So this is technically the same point as A prime. Determine and state the location of B prime if the location of C prime is 8, -3. So the first thing I'm going to do is count. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3. I'm going to connect A to C prime. So where is B prime? Well, you should notice that between AC and A prime C prime is a 90-degree angle. So I must have rotated 90 degrees about point A. So what you could do is you could take this side and this slope and just spin it counterclockwise 90 degrees. You know B is going to be somewhere up here, and a quick way to figure that out is just to count the slope. To get from C to B, I went up 1 and then over 4. So to get from C prime to B prime, you can go up 4, 1, 2, 3, 4, and over 1. And when you connect those, you should notice that those triangles are in fact congruent. That's why you should use a straight edge and not freehand it like I did right there. So the coordinates of B prime are, let's see, what is it? It's going to be 7, 1. Reason being, it's a 90 degrees counterclockwise rotation about A. And you could tell that because there's that 90-degree angle between A prime, C prime, and AC. Now the question is triangle DEF, that one right there, congruent to triangle A prime, B prime, C prime? Well, if you can describe a series of rigid motions that would map them onto one another, then you'd have an argument for that these triangles are congruent. So I'm noticing that there's this potential line of symmetry at, let's say, x equals -1. So if I reflect over x equals -1, then A would land right on D, B prime would land right on E, and C prime would land right on F, right? Because they're the same distance away from the line. So you could say that yes, they are congruent, because if you reflect over that line, they land atop each other, and a reflection's a rigid motion, and rigid motions preserve distance and angle measure. Number 14. In the diagram of the isosceles triangle below, AB is congruent to CB, so AB is congruent to CB, and angle bisectors AD, BF, and CE are drawn. So if AD is an angle bisector, that means that guy is congruent to that guy, and that guy is congruent to that guy, and CE, let's see, where's the other one? BF. So this guy is congruent to that guy as well. It tells me that the measure of angle BAC is 50 degrees. So if it's an angle bisector, I know it's cutting the angle in half, so those two angles are 25 degrees. And it's asking me to find the measure of AXC, so that obtuse angle right there. Well, now the good news is this is an isosceles triangle, so it's got congruent base angles. So I know if this is 25 and 25 over here, these two should be 25 and 25 as well. Now, if I'm just looking at that little triangle right there, I've got two base angles of 25 and 25, and I'm only missing one angle. So if I add those two angles up to get 50, and then subtract that 50 from 180 degrees, I end up with the measure of angle AXC just being 130 degrees. In the diagram below, line segment AB is drawn. Point A has been mapped to image A prime by the use of a translation. State and plot the coordinates of B prime after the same translation. So A went there, and you could just count the boxes and say, okay, I went up 1, 2, 3 up, and I went 1, 2, 3, 4, 5, 6 to the right. So for B, you can go 1, 2, 3 up, and then 1, 2, 3, 4, 5, 6 to the right. So it looks to me like the coordinates of B prime are going to be 9, -1. And if I connect those, I actually am going to use a straight edge this time. And there's a reason why. Of course, you should be using a straight edge every time when you're plotting points. What is the relationship between AB and A prime B prime? Well, they are parallel. Reason being, if you translate a line segment somewhere else, it's going to have the same slope. So translation preserves parallelism. So you could either say that, or you could say that they have the same slope, therefore they are parallel. Number 16. In the diagram below of triangle ABC and triangle XYZ, a sequence of rigid motions maps angle A onto angle X, and angle C onto angle Z, and AC onto XZ. Determine and state whether BC is congruent to YZ. Well, I think I have enough information here to state that triangle ABC is congruent to triangle XYZ. The reason being is once I read all that, I marked it in my picture, and this to me looks like an angle-side-angle proof, where I've got an angle, a side, and then the angle as well, and that's true for both these. So triangle ABC is congruent to triangle XYZ by angle-side-angle, and if you're thinking about your rules for proofs, if the triangles are the same, the corresponding parts of those triangles should be the same as well. So you can make an argument for BC being congruent to YZ by CPCTC. Number 17. Given right triangles ABC and DEF, where angles C and angle F are right angles, AC and DF are congruent, and CB and FE are congruent. Describe a precise sequence of rigid motions which would show the two triangles are congruent. Now, this information right here is just telling me that the triangles are congruent. This would actually be a side angle side proof, because I've got two angles in the side in between. But that's enough information to tell me that there is some sequence of rigid motions that would map one triangle onto the other. So it didn't tell us which direction to go in to map one onto the other. So I'll actually just start with triangle ABC. And the first thing I'm going to do, because none of the points are touching, I'm going to take triangle ABC and I'm going to translate until C lands on F. So that C prime would be there, A prime would be there, and B prime would be over here. So translating is just moving it up, down, left, or right. Now it looks to me like all we would need to do is just reflect over the line created by segment DF there, and point B would map perfectly onto E. So let's describe that. We're going to translate triangle ABC, mapping C to F and A to D. After that, we're going to reflect our new triangle, triangle A prime, B prime, C prime, over segment DF, which is going to map B prime to E. Now again, that shows that they're congruent because all we did were rigid motions, and rigid motions preserve distance and angle measure. So if they lie on top of each other, the triangles must be congruent here.